morning, grade 11s. We're going to do some practice problems in gases today. Let me just check to make sure that there's no bad reflections. No, we're good. So, today is the 48th day of Coronachem. We may get up to about 51 or so. So the first question they ask is how much gas is in the Hindenburg? Let me read the question to you.
The Hindenburg was a hydrogen-filled dirigible that exploded in 1937. If the Hindenburg held 2.0 times 10 to the 5 meters cubed of hydrogen gas at 23 degrees Celsius in 1 atmosphere, what mass of hydrogen gas was present? So we're going to assume it's an ideal gas. So we can use PV equals nRT. We're going to solve for N, which is the number of moles. Enter in all the values. The pressure is essentially 1 atmosphere. It might be just a tiny bit over 1 atmosphere, but not by much because the balloon was not filled under pressure. It's a lighter than air craft, so the purpose of the balloon is to displace a large volume of air so that it is more buoyant than the weight of air that it displaces. So the estimate was that it displaced 200,000 cubic meters of air, or at least that the cavity that holds the hydrogen gas displaced that much volume. Multiply by 1,000 to convert it to liters, so that allows us to cancel meters cubed. Atmospheres cancels with the atmospheres in the value of R, K cancels over here, and liters cancels over here. So the final answer is in moles, which is what you're looking for. That you have basically 8.2 million moles of hydrogen gas, multiplied by the molar mass of hydrogen gas. Don't forget it's diatomic. And that gives you 16 million grams of oxygen. There's a million grams per ton. So it gives 16.59, or after sig figs are factored in, 16.6 tons, metric tons of hydrogen gas were filling the empty space inside the dirigible. Second question I gave you for homework was 41 from the same chapter. The question asks, in an experiment reported in the scientific literature, male cockroaches were made to run at different speeds on a miniature treadmill while their oxygen consumption was measured. In 1 hour, the average cockroach running at 0.08 kilometers per hour consumed 0.8 milliliters of oxygen at 1 atmosphere pressure and 24 degrees Celsius per gram of insect weight. A. How many moles of O2 would be consumed in 1 hour by a 5.2 gram cockroach moving at this speed? B. This same cockroach is caught by a child and placed in a 1-quart fruit jar with a tight lid. Assuming the same level of continuous activity as in the research, will the cockroach consume more than 20% of the available oxygen in a 48-hour period? Remember that air is 21% mole percent oxygen. So 41.
so let's write down what we do know. The rate of consumption is 0.8 milliliter of oxygen per gram of body weight for the cockroach at a speed of 0.08 kilometers per hour. Actually, that's probably not going to enter into it. They just throw in that piece of information, but you don't actually use this for any part of the calculation. At 24 degrees Celsius and 1 atmosphere. So sometimes in scientific problems they'll throw in extra data and where did I put the D? Oh, the distance. Okay. It's a 5.2 gram roach running for an hour. Okay, that will enter into it. So rate times time equals distance for the roach. It's using 0.8 milliliters of oxygen per gram of roach body weight. The roach's body weight is 5.2 grams, so the amount of oxygen that's going to be consumed by that cockroach is 4.16 milliliters of O2 per 1 hour. Okay? Now we're going to use PV equals nRT. We'll assume it's an ideal gas. Therefore, PV over RT is equal to N, which is the number of moles. The pressure of the experiment at which the pressure which the experiment was conducted is 1 atmosphere, and what we found is that it consumed 4.16 thousandths of a liter. The gas constant is 0.082057 liter atmospheres per Kelvin mole, and the temperature is 24 degrees Celsius. We're going to add that to 273.15 to give us the absolute temperature. So that the number of moles that we consume is 1.70609,009 times 10 to the minus 4 moles of O2. Or, with proper attention to sig figs, which is only 2, we're going to say 1.7 times 10 to the minus 4 moles of O2 per hour is consumed.
And the question, there's actually only one sig fig, because they said 1 hour, 5 point, yeah, they said 0.08. That's only one sig fig. But anyway, I put it to 2 sig figs because it's kind of unsatisfying to write only one.
I would frame the question more carefully if I was writing it. I guess sometimes even the best of writers get a little bit sloppy and they forget that somebody's taking pictures of the house. Why are people taking pictures of the house? Okay, let's do part B. 48 hours times the rate of consumption, which is 1.706. Don't go to the rounded off answer, otherwise you're going to introduce error. Always do that whenever you continue your calculation. Continue with the unrounded number for the calculation to avoid introducing rounding error. You only round at the very end when you report the answer. So 8.189, 23244 times 10 to the negative 3 moles of oxygen is needed to keep the cockroach in the jar for 48 hours. So now we have to find out the content of the jar. Well, 1 quart is equal to, well, let's go to gallons. 1 gallon is equal to 4 quarts. And that equals 3.7854 liters. And then that means that 1 quart is a fourth of that, or 3.7854 liters per 4 quarts is what we're saying. So that means that 1 quart is equal to 0.94635 liters. I don't know why I did this complicated calculation. I could have simply looked it up. Anyway, it's never a bad idea to practice your conversion factors. So PV equals nRT, and therefore PV over RT gives you N, and therefore 1 atmosphere times 0.94635 liters the gas constant. And the temperature is 297.15 Kelvin. So what we get is that you need 3.88 this is the content of the jar of air, but remember the air is only 21% oxygen. So you've got 3.8811499 times 10 to the minus 2 moles of air times 0.21% oxygen. Therefore, you're going to have 8.150 41,479 times 10 to the minus 3 moles of O2. Not much is needed, and that's what you have. So this number is smaller than that number, and what you have is a dead cockroach. It will die because it will use more than 100% of the air. The next question I want to do with you is 43. And the question it asks is, which gas is most dense at 1 atmosphere and 298 Kelvin? And it lists 3 gases, CO2, N2O, and chlorine gas, which is diatomic CO2. So the question is kind of trivial. If we remember that a mole of any gas at the same temperature and pressure will occupy the same volume, 22.41 liters. So now the only criterion for determining which gas is densest is the one that has the highest molar mass, which is chlorine. Chlorine has a molar mass of 35 times 2 is close to 70, whereas carbon dioxide is only 44.0098, and dinitrogen oxide is 16 plus 28, so it's less than 70 at any rate. So the densest gas in that list is chlorine gas. That was a trivial question. I'm not going to bother writing in there anything on there for that. You can figure that out easily. Let's look at 49. In the Dumas bulb technique, looks like a complicated question, but if you know how to break it down, it's really not that hard. This upcoming question, it says, in the Dumas bulb technique for determining the molar mass of an unknown liquid, you vaporize the sample of a liquid that boils below 100 degrees Celsius in a boiling water bath, and determine the mass of vapor required to fill the bulb. See drawing. From the following data, calculate the molar mass of the unknown liquid. Mass of the unknown vapor is 1.012 grams. Volume of the bulb is 354 centimeters cubed. Pressure is 742 torr. Temperature 99 degrees Celsius. And all you need to do is enter it into the ideal gas law. So let's do that. So I think with problem solving, I think what intimidates students the most is there's a lot of words there, and it's hard to tell what they're asking you. But if you take the challenge of reading through the problem, sometimes you've got to read through the problem a couple times. You start seeing a pattern, and write down what the problem tells you. And very often, the fact of writing down what the problem is listing as data helps to crystallize your thinking, and you're able to figure it out. So 1049. No, I'm going to change up the marker because it's starting to get a little faded. So we use PV equals nRT, and we're solving for n again. PV over RT is equal to n. I'm going to plug in the pressure in torr, but we're going to convert it to atmospheres. The volume in liters, 354 1/1000ths of a liter. The gas constant, and finally the temperature in Kelvin. What you get is N equals 1.131 774 53 times 10 to the minus 2 moles. Molar mass is equal to 1.012 grams. And it's not the molar mass. For the molar mass, they're asking you for the molar mass. They tell you how much of the sample of the gas weighs, and they also tell you, we just figured out how many moles of it we have. Remember, the units of molar mass are grams per mole. So if you know those two pieces of information, you could find the molar mass. In this case, 1.012 grams represents this much of a mole, 1.13177,453 times 10 to the minus 2. So that gives you a molar mass of 89.4171032 grams per mole. You're only allowed 3 sig figs, so you're going to write 89.4 when you write your final answer.
And the last problem I will do with you is 65. It says, at an underwater depth of 250 feet, the pressure is 8.38 atmospheres. What should the mole percent of oxygen be in the diving gas for the partial pressure of oxygen in the mixture to be 0.21 atmosphere? The same as in air at 1 atmosphere. When people go scuba diving, the deeper they go, the less oxygen they breathe, because since the air is highly pressurized, the number of moles of oxygen present are more than adequate to meet the demands of metabolism, so you don't need to breathe in the extra oxygen. So what they do is they replace the oxygen, once you have the amount of oxygen that you need, all the other gases should be inert. So in very deep sea diving, what they do is they replace it with helium, because helium does not interact as much with body liquids, and so it doesn't absorb into the blood. So you can breathe helium at high pressure without getting, well, you can still get the bends. If you come to the surface quickly, you can still get the bends, but it dramatically lowers the risk. But when the divers breathe in that highly pressurized helium, it makes them sound like Mickey Mouse, because the helium, when you breathe in helium, we've all seen people do it with party balloons. Very dangerous job though, deep sea diving, because if anything at all goes wrong, and you're at a depth of 250 or 300 feet, you basically have a football field's length of water above your head. So good luck swimming to the surface. And even if you did, you would get a horrible case of the bends. You cannot just go swimming straight to the surface from that kind of depth if you've spent any amount of time down there. So here's 1065. So the pressure of the oxygen is equal to the partial pressure, the mole fraction times the total pressure. So you need 0.21 atmospheres. And what we're looking is, what is the mole fraction of the oxygen necessary to achieve that partial pressure when you're operating at a pressure of 8.38 atmospheres. Turns out that X is equal to 0.21 over 8.38. Units are atmosphere, so it's dimensionless, the answer. So the answer is 2.505966 times 10 to the power of negative 2. If you multiply that by 100, you can turn it into a percentage. What you get is 2.5%. So at that pressure, at a depth of 250 feet underwater, you can get away with breathing 2.5% oxygen. The air is pressurized enough that you'll get enough oxygen if you breathe a mixture of 97.5 helium and 2.5% oxygen. It'll meet your metabolic demands. Now, here's what I'd like you to try tonight to practice up. Tomorrow is Wednesday. I'll give you a mock test. Thursday, we'll mark it on the board. Friday is your last test, and then bye-bye. Have a good summer.
So here it is. This is your second last homework in grade 11, as far as chemistry is concerned. So try 1034, 40, 44, and 48. The 9th. See if you can answer all those.
And I will see you tomorrow when we review it together. And then I'll give you the mock test as well.